Drones are pretty cool, and I wanted to know how they worked, so what better way than to make one? I knew this project would be harder than usual, but I also thought to myself, this can't be that hard, right? Well, about that.
Whoa. Oh jeez.
Then for some reason I decided to set the goal of making it in 7 days. I definitely bit off more than I could chew because it took me 3.5 months. Yeah, but at least I decided to keep the drone design as simple as possible, so that would help just a little bit. The electronics of the first drone design of many consist of an Arduino Nano IoT, an H-bridge chip, brushed DC motors, and supercapacitors. The Arduino Nano IoT has Wi-Fi capabilities and an inertial measurement unit, IMU, containing a gyroscope and accelerometer, which are crucial for flight stability. The Arduino will receive commands via Wi-Fi sent from a web-based dashboard, and when it is given the command to fly, it will try to use its IMU to keep itself level. To allow the Arduino to control the motors, an H-bridge chip is used to take the signals from the Arduino and translate that to motor power. The reason for using the H-bridge chip is because the Arduino itself can't power the motors, so it sends signals to the H-bridge chip to do the heavy lifting for it. These signals tell the H-bridge how much power to give to the motors. These signals from the Arduino are called pulse width modulation, or in other words, PWM. Digital electronics like the Arduino microcontroller can only output 2 voltage levels, fully on or fully off. Here's an LED being fed these 2 voltage levels at equal time intervals. However, if I tell the Arduino to decrease how long it takes for the LED to complete one on and off cycle, we can see the LED at half brightness, while being unable to see the LED flashing on and off. Now, the second knob is used to change how long the LED is on in comparison to how long the LED is off in one on and off cycle. Here you can see that the LED is on for longer compared to when it is off. Now, decreasing the on and off cycle time, we can see that the LED is brighter than before without seeing the flashing. Now you might be wondering what that sound is this whole time. Well, a similar thing happens when applied to a motor. And finally, we have the power source, which is a supercapacitor. Now, why did I choose a supercapacitor as the power source? Well, to be honest, I was just curious to see if I could make a drone powered by these things. And that was a mistake. It was a decision purely out of curiosity and not out of practicality. To hold it all together, the chassis has nubs where the PCB holes would slide onto, and the motors would mount into a friction fit hole on the corners of the chassis. The mechanical design for a drone is pretty simple, but the software, on the other hand, not so much. So, we need to stabilize the drone in flight, which on its own has the stability of a plastic bag flying through a hurricane. So, yeah, it's not easy. The flight program would need to know exactly how much power to give to each of the 4 motors in order to stabilize itself. To help us stabilize our plastic bag, we can use the gyroscope and the accelerometer on the IMU to calculate pitch, roll, and yaw angle measurements. Gyroscopes measure rotational speed in units like degrees per second and are good at short-term angle measurements. If we multiply the gyroscope readings by the time it takes between those readings, then we get the degrees traveled in that time. Accelerometers measure linear acceleration in X, Y, and Z directions of the drone. We can use this to measure the tilt of our drone because gravity exerts a force on our accelerometer's measuring instrument, which indicates an acceleration in a certain direction. If we tilt the drone, portions of that acceleration are split into X, Y, and Z directions, so we can use trigonometry to calculate the tilt angle. Accelerometers are good for long-term angle measurements. So gyroscopes are good at short-term angle measurements, and accelerometers are good for long-term angle measurements. It sure does seem like they would definitely complement each other. Well, that's where the complementary filter comes in. This video by Brian Douglas has a good representation of a complementary filter. We take the raw gyroscope values in degrees per second and multiply by how long it takes between gyroscope readings to get how many degrees were traversed in that time. We add the degrees from that short time step and add it on top of the final angle calculation to get the angle calculation as a result of the gyroscope. We take the raw accelerometer values for the X, Y, and Z directions and use trigonometry to calculate the tilt angle based on the accelerometer measurements alone. Then we take the majority of the gyroscope angle measurement and a small portion of the accelerometer measurement and add them together. We want the gyroscope to be the main influence of the final angle calculation because it is effective for a short-term measurement. And that, my friends, is how you make 2 sensors complement each other. And it's also called sensor fusion because they, fuse the 2 sensors together. You guys know what I mean. So after applying all that in code and working on it at my university garage, just kidding, I just added some finishing touches there, I was able to get good IMU readings. I got the roll, pitch, yaw, and then the velocity Z, which is essentially up and down velocity. Velocity Z, it uses the accelerometer to get the acceleration, and then you multiply it by time to get velocity. But this is in meters per second velocity Z. And as you can see, it is not moving at 3 meters a second. So is it gonna be good even with like calibrations and stuff, because that's the nature of the sensor itself? Logically, if the drone is tilted in a certain direction, we want the motors on that side to have more power than the motors on the opposite side to counteract the tilting. Now, how much we need to power the motors falls on PID control, but I'll explain it when we get there. All this theory is good and all, but we need to first put everything together to find out if it works. However, things rarely ever work the first time, because theory can only take you so far. Everything is in its place, the PCB has been designed, but I'll have to ask PCBWay to manufacture it. I normally do this by going to the standard PCB section and putting in parameters of my PCB, like the dimensions and layers it has. Then I specify how many PCBs I want. Minimum is 5, which is good for me because I can make mistakes sometimes. I usually keep the default settings for the rest of the options, as they are good for not too complex PCBs. For this project, I need a stencil because the H-bridge chip is a surface mounted device, meaning I need the stencil to apply solder paste onto the PCB, which you'll see what I mean later. After this, PCBWay estimates how much my order will cost along with the shipping times. I send in the Gerber file, which is like the blueprint of my PCB design generated by KiCad, a PCB design software, and make the payment. Then I just wait for about 1 week for my PCB to be shipped to my door. PCBWay also has CNC milling and 3D printing services too, which is a nice addition in case I need it. This project is the most complex I've ever done. I've used PCBWay's services 4 times, and they have covered the cost of 3 of the 4 PCB iterations, so I would like to thank PCBWay for sponsoring this video. I definitely needed it. Everything arrived, though 1 day after the original 7-day goal, so that's thrown out of the window. To solder on the H-bridge chips, I applied solder paste using a stencil, which masks all the other parts of the PCB, except for the part that needs it. I put some paste down and spread it over the openings with a plastic card, then I placed the IC on top. Finally, heating the PCB to about 125 Celsius, the paste melts and makes electrical connections. After that, I solder the rest of the through-hole components with a soldering iron. To power on the circuit, I connect a battery to the charging pads, which is used to charge up the supercapacitors. Yeah, I know, it's a weird way to power the drone, but that's the cost I pay to find out if I can make a drone run on supercapacitors. So, the H-bridge IC doesn't work. Well, at least the chassis works, right? I mean, never mind. I guess that doesn't work either. Fixing the chassis is simple enough. I just got rid of the structure in the center. However, the H-bridge IC is much harder to troubleshoot. Over the course of 3 days, I desoldered, resoldered, fixed broken traces, and even got a resistor-shaped burn to finally figure out the issue. The H-bridge IC that I chose, the DRV8847, can't supply enough current to the motors. I mean, the datasheet allegedly stated that it can handle 1 amp drive current, and the 8520 coreless brushed motor allegedly stated it draws 15 amps, but I guess not. My guess is that when the motor first starts up, a single coil of the motor is connected to the voltage for a long time, making the current draw go above the 1 amp current limit and causing the overcurrent protection system of the H-bridge IC to shut everything off. However, a resistor helps to reduce the initial current spike, allowing the H-bridge IC to make the motor spin, but after the initial current spike, the current is too low and the motor's too weak, so there's no point anyways. The motor won't lift anything. I realized that at this point, that this project would be no walk in the park. However, I just need to change a few things, right? I thought that everything should be in its right place by the next iteration. Bigger and better, the DRV8871 has a 3.6 amp current rating, which is 2.6 amps above the DRV8847. I sent the design to PCBWay. They paid for my second mistake. Something felt off, so I bought a breakout board with the DRV8871 on it to do some testing. Same issue as before. Seems like an H-bridge IC is not the answer, so I tested with a MOSFET, which is like an electronic switch that allows current through when there is a voltage on its gate terminal. The MOSFET seems to work, so I guess time for another iteration. Third time's the charm, I guess. The chosen MOSFET has a 6 amp current rating, so it seems that current-wise, we're good to go. I also swapped out the smaller supercaps with the larger ones for more energy storage at the cost of weight. The motor works without the need for a resistor, so that's a good sign. However, one of the MOSFETs broke during testing. My guess is because of the sparking when laying the motor wires onto the contacts. After resoldering on a spare MOSFET, I wanted to see if this thing could fly. Only way to see is once everything is put together. Should start turning things. Yes! Some light testing showed that everything seemed to be okay. Now I went a bit crazy and decided to try and make this thing fly, and I technically did. We're good. I just want to see this thing.
Whoa. Oh, jeez.
Okay. It hopped. It hopped. It actually hopped towards us, which is kind of scary. But it hopped regardless. We just need to make it not do that. Easier said than done. But at least we got the power aspect. Okay, so somehow when I was uploading code, this thing decided to go haywire and it just flipped over like that and decided to break itself. So I guess next time I should anchor everything and also wear safety glasses. So yeah. By now, my spirits were broken, shattered, maybe even pulverized, and I just didn't know what to do. The pattern for this project was failure so far.
But why, some say, the moon? Why choose this as our goal? And they may well ask, why climb the highest mountain? Why, 35 years ago, fly the Atlantic? Why does Rice play Texas? We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too.
Now, I'm a huge space nerd, and I thought about how NASA had to figure out a lot of things by learning from their mistakes. I remembered that I started this project not because it was easy, but as Kennedy said, because it was hard. If it was easy, I would have had all the answers. So what would the point be? I wouldn't have learned a thing. Yeah, so more MOSFETs keep breaking, and I have to keep trying to desolder and replace them, and then as I do that, I physically break the MOSFETs instead of just electrically breaking them. And it seems like these motors are really drawing a lot of current, either a lot of current or having a large voltage spike, or both. I mean, it's probably both. So that's why the MOSFETs just want to die. So now I have to choose a better MOSFET. Again. And this MOSFET should work. Now, I know this seems like a pattern of thinking things should work, and then it doesn't. But trust me on this one. The AOD424 can handle 18 amps of current and 2.5 watts of power, so it should be able to handle any voltage or current spikes for this project. This PCB has to work, because PCBWay won't be paying for this 4th iteration this time around. In fact, I am the first one that ever asked for a 3rd iteration on a PCB as a YouTuber. So, congratulations to me, I guess. Okay, so for those I'll just need individual. You have to go the other way. Who knows? No. I still need, let's see. At some point, I had to replace the Arduino with a spare, and then this happened. Red 0. Oh! Crap! Oh my. I wanted to see if the drone could actually lift at all, and the only thing it seemed to do was flip vigorously. I mean, I'll count that as a trick, at least. The answer to my question that was sparked out of my pure curiosity of whether or not supercapacitors can be used on a drone seemed to be no. With much less weight and much more stored energy, the classic LiPo battery was what I replaced the supercapacitors with. Now, I didn't want to change the PCB design for yet a 5th time to incorporate the LiPo battery, so I just soldered on a JST LiPo battery connector, which were meant to charge the supercapacitors. The Arduino turns on when I connect the battery, so that's a good sign. The motors didn't want to start up. This time I knew it wasn't the MOSFETs because they worked as intended before. It had to be the Arduino and battery voltage. When the motors start up, there is a current spike, and with that, a large drop in battery voltage. This lowers the voltage that the Arduino receives, resetting it, which you can see here when the orange LED starts pulsing. To prevent this, I tested with a boost converter, which takes a lower voltage and boosts it to a higher voltage. After that, it tries to keep it there.
Hear them readjusting. So cool.
To implement this onto the drone, I had to disconnect the Arduino's power and ground pins from the PCB and solder the boost converter's outputs to them. The drone has matured. A little lighter, lasting a little longer, it is time to finally tune the drone.
Can feel it correcting the right way.
Before replacing the supercaps with the LiPo, I CAD'd a new chassis that incorporates a 1/4 threaded hole at the bottom so that we can attach it to this camera tripod for testing. With this camera tripod, I hope to be able to work on the PID controller of the drone. PID tuning involves changing the proportional, integral, and derivative terms of the PID controller to get a desired result. In this case, a stabilized drone in flight. The proportional term means that the farther we are from the desired result, in this case having the drone pointing straight up, the more power the motors put in to correct for that error. So this proportional term is directly proportional to the error from our desired result. The integral term takes the error from our desired result and adds it over time. So every second that goes by that we are not at our desired result, motors put in more power. The motors put in more power quickly if the error is larger. The derivative term is meant to prevent overshooting the desired result. It looks at how fast the error is changing, which is like seeing how fast it's getting to the desired result. And the motors counteract that by taking away some power from the previous two terms, the P and I terms. The faster the drone is getting to the desired result, the more power is taken away. All of the terms influence the end result simultaneously. How much each term gets to influence the end result comes down to what number we multiply the terms with. The higher the number that is used to multiply with a term, the more influence it has. The tuning part of the PID tuning comes down to deciding on those 3 numbers for the 3 terms. And that is the hard part. Assuming everything else, the software, the electronics, and the chassis work correctly, the drone should arrive at the desired results nicely once the right 3 numbers are chosen. I realized that the testing rig itself is not that good. I mean, it's literally a camera tripod, so I guess I need to make my own.
Bruh.
Ooh, that's good. The new testing rig seems to work well, but the drone seems to be a bit slow to respond. So that made me think that my code was working slowly. Also, when the drone needs to output high power through the motors, it just resets the entire drone, losing all control.
And now it's not responding.
So I did some troubleshooting. It turns out that when the motors are at a high enough current, the battery voltage drops below the minimum input voltage of the boost converter, and so it shuts off the regulated voltage for the Arduino, shutting it down. So I got a new boost converter with a very low input voltage and a fixed 5 volts output, which should do the trick. The drone seems to move as if it's drunk, and that's because its response time is 40 milliseconds on average. For context, the average human reaction time is 250 milliseconds. A drone needs to be able to react to changes in about 10 milliseconds in order for it to stabilize itself. Turns out, this if statement right above this function call makes the drone check if the IMU sensor is ready to take measurements 2 times in a row. It seems like that causes the drone to very infrequently go on the rest of the code that actually handles its stabilization. Seems like that broke the camel's back. After a lot of experimenting with the PID values, of course, and even more PID tuning later, things are starting to look up. It's starting to look up so much that I wanted to do the flight test. Going from instant backflips to actual attempts to stabilize itself, it seemed natural.
So I'm just gonna start.
Even more tuning created slightly better results.
Whoa. That was actually kind of good.
But it seems like the drone is at its limit. I had to change something else. And that something was the center of mass. So apparently I thought that having the battery all the way in the back of the drone's chassis would not cause any issues. But of course it did. And that was a big issue. Well, learn from your mistakes, I guess. Now we just have to put together the drone yet again.
Look at that. Perfect fit.
I've gotten really good at assembling this drone by now, so there's that.
Almost there.
With a major change to the drone, I had to retune the PID controller values, but the new center of mass changes seem to have helped a bit. At least when it's on the tuning rig.
Disturbance in the force. Let's go. Dampens out.
Apparently the performance on the tuning rig does not reflect in flight. Back to the figurative drawing board, which probably has way too many drawings on it by now.
It's not bad.
Over the course of 3 days, I made many changes, like improving the IMU refresh rate, decreasing how often the drone updates with the cloud to decrease disturbances in flight, increasing the minimum motor power for more motor responsiveness, and updating the PID values by using USB instead of the cloud to further decrease response time. There are some other code and PID control optimizations, but those were the big ones. Now the drone might seem a bit jittery from the changes, but that's probably from the increased motor response time. But despite the jitteriness, it actually surprised me when I tested it in flight.
Oh, look at that. Oh my goodness.
Now this is the best attempt that I ever got in this project. A whole 3 seconds of sort of stable flight. Then I proceeded to test the drone to the point that it broke. So yeah, that kind of ruined the celebration a bit. In particular, the antenna broke, so that really sucked. After replacing yet another Arduino, I tested some more, but the results just weren't as good as the 3-second attempt, and I finally decided to give up after 3.5 months. I figured that it was more of a hardware issue with the fact that I used brushed motors, which are not as responsive or effective enough for self-stabilizing quadcopters, other than for RC-controlled toy quadcopters where the user can actively correct for drift. This project taught me a lot about engineering, which is that you will very rarely get things right the first time around, because real life is a lot more complex than equations, simulations, and theory. To get the project to work in real life, you need to learn about how it works in real life. And the only way to do that is to fail for real and learn from it. Even though I only made a partially functional drone, I learned a lot from it, and I will definitely come back again in the future to try and make a better one. So why did I start this project in the first place? Well, it was a good challenge, but in all honesty, I was just curious.